So welcome everybody to this latest instalment of the Oxford Discrete Maths and Probability Seminar. So it's a huge pleasure to have Bastien Mallein, who's speaking to us actually from Montreal, although he works in Paris. And he's going to speak to us about the infinite bin model and the longest increasing path in an Erdos-Rényi random graph. Over to you, Bastien.
Well, thank you very much for the invitation, for being here to listen to me. So I'm going to talk about this problem, which can be related to a question of how long does it take to make a complex task if you have a lot of people that can do it. So let's start with an example. So an apple pie recipe, for example. So if you want to make an apple pie, so you have a certain number of steps that you have to follow, right? You have to preheat the oven, prepare a dough, and flatten it and put it in a plate. You have to peel some apples, cut them into pieces, put the pieces over the dough, and put everything in the oven. So let's say there are 7 steps with mostly like a similar time amount for each of them. And so I wonder, how long does it take to bake that apple pie? So if we just have one cook, then the number of steps needed is exactly the same number as the number of steps in the recipe. So Alice will come and will do every step one at a time. So if a second cook comes, then you can start dividing and parallelizing the work. So for example, while Alice is preparing the dough, Bob will start preparing the apples or the opposite. And so you can reduce the total number of steps needed to realize your recipe, right? And you can bring more and more cooks. And by adding cooks, you can reduce again the amount of time needed. So if you add a third cook to prepare your apple pie, so Alice will, for example, take care of the oven, Bob takes care of the dough, and Craig takes care of the apples. But then you run in some problem, right? If you add the fourth one, well, you cannot start cutting the apples until they are peeled. You cannot start flattening the dough until it's prepared. You cannot put everything in the oven before the elements are put together. So you have a limited number of steps that you can parallelize, and at some point you run out of things to do to your extra cooks. So well, how do we compute this minimal number of steps needed to realize this recipe? So a way to do it would be to represent my recipe as a graph. So the graph will be ordered, and I will add edges between the vertices of the graph, which represent dependencies between tasks. So the idea is that, for example, task set is to put the apple pie in the oven, and for task set to be doable, I have to have preheat the oven, which is task 1, and I have to have put all the ingredients into place, which is task 6. So task 7 depends on task 6 and task 1. And the idea here is that my graph has to be without cycles, because otherwise, I mean, if you have a cycle, then you cannot do it. It's so it's basically an administrative task, right? You have to get your healthcare, but to get your healthcare, you have to have an address, and you have an address, you have to ask the banks, which ask you for an healthcare for healthcare. So then you cannot do it. So a complex recipe will have no cycles if the task is doable, and you can represent all the dependencies by oriented edges. I claim that a very simple lemma is that if I have infinite number of people available to me so that I can parallelize tasks as much as possible, then the minimal number of steps needed to realize the project is equal to the length of the longest path in this graph. So for example, when we had 3 cooks or more, we needed at least 3 steps, and we have a graph of length 1, 2, 3. I mean, we have a path of length 3 in this graph, so it's working, right? The longest increasing path is of length 3. So now, I would like to generalize this thing and consider a large project with a lot of dependencies. And that's where Barak-Erdos graphs come, which are oriented version of Erdos-Rényi graphs. To study the longest path in this graph, I will introduce an intermediary model, which is the infinite bin model. And by coupling these two models, I will deduce elements on this problem of finding the length of the longest path in the Barak-Erdos graph. Okay, so the Barak-Erdos graph, so as I said, it's a directed version of the Erdos-Rényi graph, where you have a set of edges, which is the integers between 1 and n. And for every edge ij, you add an edge from y to j with probability p, independently of any other edge. So every time the edges are oriented in the increasing order of the vertices. So you can define this graph on integers between 1 and n, but obviously you can also define it with set of vertices equal to the whole integer line, right? So, okay, so this is an example of a Barak-Erdos graph. So my first vertex is connected to a random number of vertices to its right, and then independently, every other vertex will be connected to a random number of vertices to their right. And so the question that we're asking, so analogous to my cooking recipe, is how long is the longest path in this graph? And here, for example, we have a path of length 1, 2, 3, 4, 5. Okay, so my question will be to study this length ln of p in the large n limit. So I will fix a value of p, so I will have a dense graph with a lot of vertices, and I ask, how long does ln of p, how long ln of p is? So the model of this directly the loop-free random graph was introduced by Barak and Erdos in 1984. So that's why we call it that way. But they were not interested in studying this longest increasing path, but it's one of the most studied features in this model. And it's used as a way to evaluate, for example, the performance of computer systems. So that's my short story about parallelizing. But it's also used in a food chain problems. Like I have this complex network of animals with other animals, and I'm wondering what is the longest food chain, which would be, for example, the most sensible to fluctuation in the environment. And it has also a nice interpretation in terms of queuing theory, and it introduced a class of Markov chains with long memories, but yet you have renovation events that you can define. So it's interesting in these settings as well. Okay, so I claim that if you look at the length of the longest path in this Barak-Erdos graph, then it's not too difficult to convince yourself that this should grow linearly with n. I mean, intuitively, it makes sense, right? You have finite length, so you can find path that grows linearly with n, and you cannot have more than n vertices in it, so it has to be more or less linearly. But in fact, ln over n converges in probabilities to some constant c that depends on p. So this you can see it, for example, using that ln, it will be a subadditive ergodic sequence, right? The length of the longest path between 0 and n is certainly shorter than the longest path between 0 and n over 2 plus the longest path between n over 2 and n, which will be 2 independent copies of ln over 2. And this function c has some interesting properties that were discovered by Newman. Notably, c is continuous, increasing, and its derivative at point 0 is equal to e. So, okay, here is the graph of this function c. So you see that it's not exactly a concave function, right? It's debatable if this is a convex part of the curve, but it has some nice properties, and the function c of p over p is quite nice as well. So you see that not only c of p over p goes to 0 as p goes to 0, but in fact the derivative there is infinite. So c of p over p is decreasing, which I think I understand why, but it's convex, and I have no idea how to prove that this function is convex. Why does c of p over p is convex? I have no idea why. Okay, so well, the nice properties of the function c were started to be studied by Foss and Konstantopoulos, who, for example, they obtain a nice upper and lower bound for this function, which I draw on this graph over here. So you see that their approximation is very tight for p in neighborhood of 1, and this tight estimation of this function c allows you to obtain the Taylor expansion of c around 0.1 up to little o of p to the 4. So it's interesting because when you look at this c of 1 minus c, you see that the coefficients are alterning and are all integers. So now the question is, well, can we go further and try to get the Taylor expansion of this function c at with some larger parameters? So the answer is positive. So together with Sanjay Ramasamy, who's currently at the IHES and the CNRS, we studied from the infinite beam model perspective the question of longest increasing path in the Erdos-Rényi graph. And we were able to find a sequence of upper bounds and lower bounds, UK and LK, that converge exponentially fast to the function c, but exponentially fast like 1 minus p to the power k. So using the Taylor extension of my lower and upper bound, which are just very nice ratio of polynomials, we were able to compute the Taylor expansion of the function c up to well, a large order, in theory up to any order, but in practice only up to a finite number of order before the computer starts crashing. But we were able to get a Taylor expansion that was quite long. So for example, it's this one over here, 1 minus p plus 1 minus p squared, and you have minus 3 plus 7 minus 15 plus 29 minus 54, etc., etc. And this sequence has been, we registered it to the Open Encyclopedia of Integer Sequences. And so what we proved afterwards, what actually the function c is analytic on 0, 1, so except at 0.0. And you have a decomposition of c in integer series around 0.1, which is converging on the interval 3, 4, 1. And all the coefficients are integers. So we are not sure that there are that it's really an alternative sequence. So we don't exactly know that. We don't really know that ik is the absolute value of ik is increasing, but we strongly believe both of them are true, and we believe that ik grows exponentially fast. So the radius of convergence of this series is not 1. So the radius of convergence of this series is smaller than 1, but we don't have an exact value for it. Okay, and so maybe the third part, and what is a bit weird when you see that C of P seems to be so nice and analytic, is the asymptotic behavior of C of P when you're in the neighborhood of 0. And in the neighborhood of 0, C of B behaves like E times P to the fourth order. But then you have a correction as minus pi squared over 2 p over log p squared. And this second order correction is related to a model of branching random walk with selection. Okay. So, okay, maybe answer some questions so far with the model? Well, if not, then I can start to introduce the intermediate model that we introduced to work with this question. So this is the infinite bean model. So the infinite bean model is a very simple model of balls and beans. So you put an infinite number of beans on Z, and you start with a configuration where you have put a certain number of balls with an important fact is that all beans to the right of a certain place are empty. So you need a front of beans, like a rightmost ball in my configuration. And so what you do is that at every integer time n, you add a new ball to the right of the science rightmost ball in your system, where psi n is an independent random variable, integer value random variable. And we take interest in the speed of this front of bits. So for example, if at time 1 I have psi1 equal 5, then I count the number I enumerate my balls from the rightmost one to the leftmost one. I find where is the fifth rightmost ball in my bin configuration, and I add the ball exactly to its right. And then I start over again, right? So psi2 is equal to 4. So I enumerate my my balls. So you see that there was a ball that was formerly labeled 5 is now labeled 6. And the ball that I just added is the ball labeled 4. So I will add a new ball to the right of the ball labeled 4 over there. And you can continue psi3 equals 7. So I find the ball currently indexed 7, and I add a new ball to its right, and so on and so forth. Okay, here. And now we take interest in the speed of throughput. So you see that as time evolves, you will add new ball in previously empty bins. So over time, you expect that the position of the rightmost ball will drift to the right at some linear speed again. And what I'm claiming is that the speed of this infinite bin model will be related to the function C of P in my Barak-Erdos graph. So this model, this infinite bin model, was introduced, studied by several different authors under different names. For example, Aldous and Pittman studied a version of this model where psi is a uniform distribution on the integers between 1 and n. So there, at every step, you choose one of the n rightmost bin, one of the n rightmost balls, sorry, and you add a new ball exactly to its right. And actually, this model was a model that you can think of as a continuous time branching random walk, where you have particles that reproduce independently at exponential times, but at every time, if you have more than n particles, then you immediately kill the leftmost one. And so the model of Aldous is really can be thought as a continuous time version of the infinite bin model with uniform distribution. And the generalized infinite bin model was studied by Foss and Konstantopoulos, where they proved that if you assume that the expectation of psi, the index at which you put balls is finite, then this model exhibits renovation events. So basically, those renovation events tell you that I know that after some time, all my future balls will be placed to the right of some existing bin. Right? I will have a ball indexed 1, and all the balls after that ball will be placed either as children of the ball index 1 or as children of their children. And those renovation events are quite useful when you want to prove, for example, central limit theorems and things similar. Okay. So, well, let me introduce maybe some notation. So I will write X, my configurations of infinite bin model. And for each K, I denote by psi K of X, the configurations which consist of adding a new ball to the right of the case rightmost ball in X. So then it means that for my infinite bin model, I can define xn as the function psi n applied to my configuration xn minus 1. So it's a way to formalize this Markov chain. And what is interesting here is that you can construct a partial order on the space of configuration, so such that the function psi will be both decreasing with respect to k and increasing with respect to the configuration. And so the partial order of configuration is that I will say that x is smaller than y if for every integer I find that there are more balls to the right of index k in y than to the right of index k in x. So you look at the cumulative distribution function of x and y, and if the cumulative distribution function of y is larger, then you say that y is larger than x. Okay. And so using these properties, you can now couple your infinite bin model so that if the configuration x node is smaller than the configuration of y node, and if the reproduction law psi of the process y is dominated, zeta y, sorry, of the process y is dominated by the stochastically dominated by the one of the process x, then you have a monotone ordering of your system, and so you can compare infinite bin models with different reproduction laws and different initial configuration. And this is quite useful to prove the fact that the front of your infinite bin model has an explicit speed, which is a fixed random variable, right? A fixed constant. It's not a random variable. So if you look at the value, the front at time n in your infinite bin model divided by n, this converges to a constant that depends on the law mu. Okay, so the proof of this fact is quite simple. So the idea is that, well, first, if you assume that your measure has finite support, then actually you can look at just a reduced Markov chain. You just need to know the relative position of the k rightmost balls to know what is happening near the tip, right? And so it's basically an analytic theorem that will tell you that, okay, this process has speed. So now the idea is that, well, when mu has no finite support, then I know that the infinite bin model with a reproduction law mu will go faster than the infinite bin model with reproduction mu k, which is basically, so when I ask to add the ball to the right of a bin of some index, if the index is smaller than k, then I add a ball, and if it is larger than k, then I don't add a ball. Because I put fewer balls, I know that I will go slower. So the expected speed has to be larger than this v mu k, the speed of the infinite bin model with just a finite support. So v mu k, I know that it exists. And so now I need to get an upper bound. So I need to find a way to guarantee that when I add a new ball, then I go slower than something that I can control. And the idea is that, well, to get an upper bound, you just do the stupidest thing possible. So if so for your upper bound system, you say, well, okay, if you ask me to add a ball to the right to the bin of index k, what I will do is that I will shift my full configuration by 1. So I modify and I introduce a lot more particles. But the idea is that this shift only contribute to some deterministic speed, which is mu of k plus 1 infinity. And this quantity will be as small as you wish when k goes to 0. So it's clear that this speed v mu does exist as the limit as k goes to infinity of this v mu k. And incidentally, that's how we got the upper and lower bounds of our infinite bin model, which allowed us to get the Taylor expansion through the analysis of invariant measure of some well-defined Markov chain. Okay. So now maybe let me go back to the coupling between this infinite bin model and my original problem of longest increasing path in an Erdos-Rényi graph. So, well, what I'm claiming is that if you want to compare the two models, you just need to look at the infinite bin model with geometric distribution of jobs. So the idea is that you start coupling the two models by saying, okay, so my infinite bin model will start with an infinite number of balls at position -1, and my Erdos-Rényi graph will start with the empty graph. And what I do is that at every step n, in the Erdos-Rényi random graph, I just add the new vertex with all its connection to the previous vertices. And in the infinite bin model, I add a ball with a bin whose index is given by the length of the longest path in the graph that ends at vertex n. And what I'm claiming is that this bin configuration is an infinite bin model with geometric distribution. And so in particular, my function C of P is equal to this V associated to the geometric distribution. Okay, so how does this work? So I have my initial bin configuration with an infinite bin number of balls at position -1 and my empty graph on the top. So I start with by adding the vertex 1 in my graph. And so I wonder, well, what is the length of the longest path ending at vertex 1? And well, it's a part of length 0 that starts from 1 and ends at 1. So I add a new ball in the bin index 0. Now I add my second vertex 2, and 2 is not related to 1. So the length of the longest path ending in vertex 2 is again, oh, sorry, no, there is a vertex. Okay, so there is a vertex, sorry, between 1 and 2, sorry. And so the length of the longest path ending at vertex 2 is exactly equal to 1, right? I have this path of length 1 between 1 and 2. So I add a new ball in the bin index 1. Then I add my vertex 3. So let's say that 3 is connected to 1 but not to 2. While the length of the longest path ending in vertex 3 is exactly equal to 1 again. So I add a new ball in the bin index 1. So now my vertex 4 is connected to no one. And I see there is a question.
Yes, Bastien, sorry. How do you decide which vertices are connected? Sorry.
So it's based on the definition of the Erdos-Rényi graph. So for each vertex, I add a connection with priority P to every of the previously present vertices. Right. So for example, here I had priority P cube not to be connected to either 1, 2, or 3. And so because 4 is connected to no one, then the length of the longest vertex ending at vertex 4 is equal to 0. So I add a ball in the bin indexed 0. Okay. So now let's think about it. So what does this dynamics tells us for the bin model? So the idea is that I have my vertex 5 here, and I look with priority P, it can be connected to any of the previous vertices, right? So it can be connected with priority P to the vertex 3. And if it is connected to vertex 3, then I know that the length of the path ending at 5 is equal to the length of the path ending at 3 plus 1. And if it is not connected with 3, so with priority 1 minus P, it has again priority P to be connected to the vertex 2. And because it is, if it is connected to vertex 2, then it will have a path of length 2. So I will add again a ball in the bin of index 2. So you see that really what I'm doing is that I'm saying, okay, so with priority P, I'm connected to this ball. If I'm not, then with priority P, I'm connected to this ball. If I'm not, then with priority P, I'm connected to this ball. And every time, if I am connected to the vertex corresponding to a specific ball, then the length of my longest path ending in my position will be equal to the length in the previous one plus 1. So I will add a ball to its right. So it's not really why there is this connection between those two vertices. So for example, here my vertex 5 is connected to 3. So that my longest path is the length 1, 3, then 3, 5. So I add the ball in the bin index 2. And you can continue your description. So for example, vertex 7 is connected to vertex 6, which has a path of length 2 connected to it. So it has a length at least 3. And in fact, it has length exactly equal to 3. So that's where this coupling between the infinite bin model and the Barak-Erdos graph comes from. Okay. So now, well, okay. Sorry. So now how were we able to prove that this function is analytic? So the idea is to use the connection between the function C of P and the length of the infinite bin model. So we claim that because we have this Albrecht convergence and domination, then we know, in fact, that C of P can also be computed as the limit of 1 over n, the expectation of Fn. And we will prove that this expectation can be computed as a sum of independent contributions, at least for P close enough to 1. Okay, so heuristically, what happens? Well, assume that P is very, very close to 1. Then up to little o of 1 correction, by sequence of different jumps is exactly 1, 1, 1, 1, 1, 1, 1. I have a 1 with priority 1 minus P, which is up to a little o of 1 equal to 0. So basically, I just add at every step extra bin to the right of the currently rightmost bin. So my infinite bin model is just, well, I add balls to the right at rate 1. Therefore, C of P should be 1 plus a little o of 1. Okay, so now let's look at the correction, right? So if I look at little o of 1 minus P, then at some rare times, I will see some 2's in my sequence. And what is the effects of the 2 in the sequence? Well, it's the fact that I put a new ball atop of an existing ball instead of adding it to its right. So I reduce a little bit the speed at which I am going to the right. Therefore, C of P should be to the first order, to the second order, 1 minus the probability of adding exactly a 2 in my sequence plus a little o of 1 minus P. And I can continue and try to see, well, what are the 1 minus p squared corrections to my system? So what happens with a probability of order 1 minus p squared? Well, what happens is that you start to see features which are 2 2s in a row at some rare times, and you start to see 3s in your sequence, right? And so what happens? Well, if you see 2 2s, the first 2 is building atop on the existing 2, so I'm moving slower than expected, but the second 2 is actually going to the right because, well, it is built not on the rightmost ball, but on the second rightmost ball. So if I just say that for every 2 I remove p1 minus p, then I removed a little bit too much, and I need to add 1 for every pairs of 2s in my sequence. And obviously the 3s are not helpful because they are put so far back on the right. And so you can decompose it and say C of p is 1 minus the number of 2s plus the number of pairs of 2s minus the number of 3s, and you can expect to keep expanding like this. Okay, so that's exactly how we do this computation. So what we do is we say, okay, my function C of p, it can be written as a sum for all integer value features of some epsilon, which takes value in minus 101 times the probability of observing exactly this feature. And because psi is geometrically distributed, this probability is just a polynomial. So up to rearrangement of terms, you will see an entire series in 1 minus p. Okay, so, well, this function epsilon, so maybe I don't need to give too many details, but the idea is that for every pattern, you can define d of u, which is the distance that you travel away from the front by moving, by first doing the step u of 1, then u of 2, then u of 3, then u of n. So this is d of u, it's the distance traveled by doing my sequence of numbers. And I claim that d of u can be written as the sum for all my subpatterns in u of this contribution epsilon minus 101 of all the subpatterns. So every word can be decomposed in subpatterns. And okay, so it's not immediate to solve this equation in epsilon, but you can actually do it by looking at epsilon as some kind of Laplacian on the words. So the idea is you look at delta of u, which is d of u minus the d of u when you remove the last number. So d of u is either 0 or 1. Delta of u is exactly, so if I do my series of words, do I add a ball in a new bin at my last step or not? And if I define var pi of u, the pattern obtained by forgetting the first letter, then I claim that my number epsilon is exactly delta of u minus delta of u where I forgot the first letter. So it's a number between minus 1, 0, and 1, and I can verify that this formula over here holds. And because this formula over here holds, I can apply it to a d of psi1 to psi n and compute the expectation. And this formula will appear quite immediately as well some kind of a Cesaro computation.
Sorry, quick question. The definition.
Yeah.
That's how much the front moves when you do pattern U, assuming what shape is behind the front, because doesn't it depend on what the shape is?
That's a very good question. So it really depends on the starting shape. And what I'm claiming is that no matter the shape, every shape will give you a different configuration, but all of them will give you the same answer.
The same answer for...
So you have the same entire series in the end, but represented as a sum of different epsilon u's. So you can start, you can define this displacement starting with initial configuration with an infinite number of balls at position -1, or you can start with the initial configuration, which is balls at every negative integers, right? One ball at every negative integer, or any other configuration like this, and all of them will give you a different function d of u, a different function epsilon of u, but yet, no matter what starting configuration you defined, this representation over here this C of P will be equal to the sum of the expectation of epsilon of psi1 psi k for every k, right? And psi is a family of RID geometric random variables. So C of P, right? I write it as the sum for every word of this epsilon u, p to the power the number of letters in u, 1 minus p to the power the sum of the u of j minus 1. And well, I'm not claiming that there is a unique sequence epsilon that is that can be used to represent my function C of P. Every starting configuration gives me a different representation of this series. But the idea in the end is that we want just to get C as a power of 1 minus p to some powers, right? You want to represent it as a sum of ak 1 minus p to the k. So if you do this, then you get a unique representation. That's what's happening. Okay, so I mean, do I answer your question or not?
Yeah, thanks.
Okay. So yeah, okay. So just to recap quickly, right? So I defined this connection between the Erdos-Rényi random graph and the question of wondering what is the length of the longest path in this graph with this infinite bin model, which is a balls and bin model, which can be thought of in some sense as a rank-dependent branching process. And well, what we claim about the function C is that the function C is analytic on 0, 1, and has a very nice series expansion around byte 1 with integers coefficients. And the function behaves as e times p times 1 minus pi squared over 2 log p squared around p equals 0, so very non-analytic at point 0. And well, we find some very nice open questions that I have no idea how to work with. So for example, does the function which p goes to C of p over p is convex? I have no idea why it looks so true, but it's so unclear. Is my series of coefficients ak, is it growing absolute value? Is it of alternating size? We have no idea. So radius of convergence of this series, we don't know it either. But okay, so another nice extension of it that we started to work with, but we are still making progress is, well, I started with an infinite number of cooks to make my very hard recipe. What if I have only exactly k cooks? Can I define a function ck of p and can I study its properties? And are they similar or not too similar to the ones of to this? I have no question. Well then, thank you very much for your attention.
Thank you very much, Bastien, for a lovely talk. So we've got quite a bit of time for questions. Perhaps I can start by asking one. So if you could go back to your previous slide, you've got this expansion at 0, and you said something rather intriguing about its relation.
Oh, sorry, I'm lost. Okay, sorry.
So you have your expansion at 0 being EP1 minus pi squared on 2 with the log squared p on the bottom.
Yeah.
And you mentioned something briefly in passing at the start of your talk about how this was related to a branching random walk with selection.
Yeah,
Are you willing to tell us a little bit more about that?
Yeah, okay. Well, okay. So it's very quick, right? But the idea is that when you look at the geometric distribution with very small parameter p, well, if you concentrate on the beginning of the sequence, this sequence starts to look like a uniform distribution of the number between 1 and absolute value of integer part of 1 over p. And so the idea is really to formalize this connection, to say that, okay, I can really do a very nice coupling between the infinite bin model with geometric distribution of small parameter p and the infinite bin model with uniform distribution. Well, okay, as I mentioned, this model of infinite bin model with uniform distribution was studied by Aldous and Pittman. And if you look at this model in continuous time, what you really see is you see a continuous time branching random walk where you have a system of particles that are not moving, but at rate 1, they create one child exactly one step to their right? And every time there is a branching event, you kill the leftmost child. So it's a branching random walk with selection. And branching random walk with selection, well, they were studied quite a lot, notably by by Bruni and Derrida, who predicted a lot of orders for the asymptotic behavior of the speed of this system. But Berard-Aguirre, they give a very nice estimate of how does this speed goes to the critical speed as n goes to infinity. And well, okay, so yeah, I put way too many details, but the idea is that if you write Wn, the speed of the infinite bean model with uniform distribution on the integers between 1 and n, well, Wn will behave like e minus pi square over 2 log n squared, something like this, right? And you have a connection between C of p and W of the integer part of 1 of p. So that's why you have this epsilon, this e times p times 1 minus pi square over 2 log n squared. That's more or less a connection.
Thank you. Does anybody else have any questions?
Can I ask a quick question?
Jeff, go ahead.
If you go to page 12 of your slides,
yeah,
probably just a trivial point or something I'm missing, maybe.
Yeah.
So is this right, this equation you have, or is there some typo? Because as p goes to 1, it seems the left hand side's going to 0 and the right hand side's going to 1.
Yeah, sorry, it's C of p. Sorry, yeah, it's C of p. Sorry.
Right. But that's what I thought. But then it's strange because then you're talking about what happens when p is close to 1, but in your picture, you have the upper and lower bound sort of near 0.
1. No, you have them near 1, right? I mean, near 1, the three curves are so close that they are actually all together, right? The C of p curve is in red, and the lower bound is in blue, and the upper bound is in yellow. But they are so close around p equal 1 that they are all draw atop one another.
Okay.
I would have to zoom in quite a lot to see the difference between the three.
Okay, thank you.
You're welcome. And so actually, you know, when we look with your sequence of upper and lower bounds, so those are basically the speeds of this infinite bean model with geometric distribution, where you ignore all the moves that are larger than p. And what's quite interesting is that you see that the lower bound is usually much better than the upper bound. The lower bound, even L3 of p, is a very good approximation of this C of p. So we really expect that the Taylor expansion of C is very close to the Taylor expansion of Lk of p for quite a small value of k. But the problem is that to compute analytically the function Lk, we need to get the invariant measure of this quantity, which is the invariant measure of a Markov chain with of order 2 to the k sides. So it's quite expensive, and I think we capped at L. I might say something wrong. So I think we capped at L12. We have an analytic expression for L12, but we are able to get all its analytic expansion, but we can only prove for the first few factors, the ones that are close enough to the upper bound, that we have the Taylor expansion around 1. But we believe that actually this Taylor expansion is true on a much longer scale.
Any other questions?
Yeah, can you say a little bit more about the K-server model that you mentioned at the end? How's it?
Yes. Well, so it's quite difficult to define exactly the model. So the idea would be to do the same graph and say, okay, so now I have my K servers, and so what I do is that I can parallelize up to K tasks at the same time, and I try to realize all the tasks described in my task graph in as few steps as possible. But if you do this, you have more or less two ways of doing it, right? You have a greedy way, which is, okay, I will at every step do the K tasks with the lowest rank that are currently available to me. Or I can try to look forward in time and see, okay, I will do the K task that will free me up as many tasks as possible in the future. And it's not clear yet. I mean, one is easier to study, and the other one is probably the one that we would really want to look at, right? So,
I mean, looking into the future, you could look. I mean, looking different distances ahead. I mean, if this
you look some steps ahead, and you say, okay, so I could do those 2 tasks, but actually, if I do this one, then 2 steps down, I will have free me 2 steps to k different tasks, and therefore it's better to do one that is not the lowest rank one, but the one that you will free me as many dependencies as possible, right? So I don't know exactly what is the right way to frame it. And in particular, there is definitely no connection, not a simple connection like this with a quantity like the longest increasing path, right? It's more about the number of different long paths and how many of them are not interconnecting. So it's quite a different question there.
Is it obvious that it would even stabilize if you look further and further into the future, that it couldn't just keep flipping between?
My understanding would be that you have those renovation events, right? So at some point, every dependence to the right of some point will depend on a single task that you need to do. So if you have enough renovation, renewing, I expect that this CK of P should exist. And the existence of this function, this I believe is true. As does the optimal strategy stabilizes? This I'm not sure.
Okay, thank you.
Yeah, you're welcome.
Anybody else?
Yeah, so in the original, you had in the original question about just along with part in the graph, you had P constant then goes to infinity. I guess it's just a completely different flavor question. You know, what about P is function of n, 1 over root n, or whatever function of n?
No, it's very interesting actually. The question P goes to 0 is quite interesting. So you go P goes to 0 and n goes to infinity. I believe that as long as P goes to 0 slow enough, you're in the same regime with this branching random walk with selection thing, right? You will see this minus pi square over 2 log Pn squared now that is playing a role to get the asymptotics. But there's clearly a rate where you start to go to 0 fast enough with respect to P, so that there you start to get from branching random walk with selection to classical branching random walk. And so you would have like P times E, not 1 minus 1 over log P squared, but 1 minus constant times log P. So you have a phase transition here. I strongly believe that it is around P of order log n to the cube over n, but I have no way to compute it exactly. Right? I believe it's here, but yeah, I don't have any formal proof for it. So it's quite a difficult question. You have to look at you have to start to look at different models somehow. At some point, it becomes easier, for example, to look at the length of the longest path starting from vertex 0 than the length of the overall longest path. Because your graph will start to disconnect and you will start to see like independent subgraphs. So yeah, the question becomes more difficult when P is small. So that's why we didn't look at it too much.
So you said you think P is log n cubed divided by n. You think is the transition? Is that right?
Yeah. I believe there is a transition here. I mean, okay, maybe I'm not. I don't have the right. Okay, so the first order, Newman obtains the first order in any regime, right? The main order, this ln over n, it has an estimation of ln of Pn when n goes to infinity and P goes to 0 at any regime. But if you want to look at the corrections, correction to this main order, there you have a phase transition, and I believe this phase transition is around log n cube over n.
Great. Any further questions? In that case, I'm going to stop recording and propose that we unmute and